All right, class, I thought I would go ahead and make a video on Chapter 15 in the Chemistry 130 course to help us prepare for the exam in case I run out of time during lecture. So Chapter 15, we're going to take what we learned in Chapter 14 about organic chemistry and apply it to biochemistry. So we're looking at the chemistry of biological systems, and we start with the organic chemistry substances, but we're going to give them some different labels in biochemistry. So the first thing we'll notice is the let me see here. Is what are the biologically important molecules? What are lipids? Also, we think of those as fats. What are proteins? You're going to see nitrogen plays an important role in proteins. What are carbohydrates? And then we're going to skip section 5.5 on nucleic acids. So you've seen something like this before. Maybe the difference is that we didn't have all of those OH groups that you see in the compound. So you, oops, let me see if I can get a better pen color too. I actually thought it would be red. Well, apparently not. All right, so looks like something we've seen, right? 3 carbons, that would be propane. And then we have these hydroxy groups, which you think of as generally as alcohols, but we haven't seen one where we have 3 hydroxy groups on the compound. And so when we see hydroxy groups bonded to this backbone that we kept talking about, that the alkanes have a backbone, carbon has a backbone, and these are the functional groups that determine the chemical and physical properties of the compound. And this type of compound is called a glycerol. So glycerols, you generally probably associate those with soaps, but they also have these OH groups which make them taste sweet. So sugars, alcohols, glycerols, that's something that's going to be in common with all 3 of those, is you'll have these hydroxy groups. And the thing about glycerols, they're 3 carbon chain there. All right, fatty acids. So fatty acids, what I want you to focus on from chapter 14, they're carboxylic acids. So what we know about carboxylic acids is that you have a carbon with a double bonded to an oxygen, and then you have an OH group here. So that's called the carboxyl group. And then the carboxyl group is bonded to usually some alkyl group, R, and the one that we're going to focus on the most probably is CH3COOH, and that would be acetic acid. All right. So the fatty acids, the more common ones, is butyric. So notice it's 4 carbons, and so 4 carbons would look like 1, 2, 3, 4, double bond here, OH here, a hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here. So let's make sure this is right. We have C, 1, 2, 3, 4. We have 3 plus 2 plus 2 plus 1. We have 8 hydrogens, and we have 2 oxygen. So butyric acid, rancid butter, and so forth. Now we haven't talked about C16 or C18, but C16 is called, with the, again, the carboxyl group is called palmitic acid. And again, you'll probably hear this, probably derived from a palm tree. And it's something that you'll see in food products. Stearic acid, C18, H36O2. These are all saturated acids. Remember what saturated compounds are? They have carbon-carbon single bonds, not carbon-carbon double or carbon-carbon triple bonds. So these are all saturated fatty acids. And then we have a couple examples of unsaturated fatty acids, and that means somewhere in the structure there's at least one double bond. But again, all of these acids, what they have in common is they must have the carboxyl group. All right, so the next group of compounds we want to talk about is amino acids. These are the precursors to proteins. So amino acids, generally they have both an amino and a carboxy functional group. So, and then the R group determines what type of amino acid we're dealing with. So you know that ammonia is NH3, and we talked about that if you substitute out one of those hydrogens for another group, that makes it an amine. And so then we see the carboxy group here, and that makes it an acid. Again, why does it make it an acid? Because this is a non-metal hydroxide. This hydrogen can leave, the hydrogen ion can leave. So that's what gives us the acid properties. So what you find with amino acids, this part pretty much remains unchanged. This part pretty much remains unchanged, and what defines the amino acid is what R group is attached here. Yes, these are the active sites, but usually we think of this R group as the group that determines which amino acid we're dealing with. All right, so the next thing we have is sugars. So you've heard of sugar. What is a sugar? Well, it's water soluble, typically sweet. It's an organic molecule. It's either a ketone or an aldehyde. All right. And so what do they look like? Well, you notice, first of all, they're long chains of carbons. They're more than 3, so they're not a glycerol. But they do have the hydroxy groups like a glycerol. And then you see this end on here and you go, oh, what does that mean? Well, it's got to have 4 bonds, right? So you're going to have the 1 carbon bond here. You're going to have a hydrogen bonded here. And you're going to have a double bond on the oxygen. So if you wanted to see what that looked like, it would look something like that. And then you go, oh, when I see this, and I see this hydrogen carbonyl group, and then this alkyl group here, I definitely have an aldehyde. So this sugar would be an aldehyde. This part down here, you know that would be a carbon. There'd be 2 hydrogens, and then this OH group coming off of it. So that is what determines this to be a sugar. And so what would we call this? Well, we got 1, 2, 3, 4, 5, 6. So we've been writing this as C6H12O6. Let's see if that works out. We got 1 hydrogen, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's where we get to 12. And then 6 oxygen. 1, 2, 3, 4, 5, 6. So this is the chemical formula. This is the structural formula. And the thing about a sugar is it can bond with itself, and then we get, in water, we get this type of sugar, a monosaccharide. All right, we're going to skip the phosphates. So the phosphates are really important when we talk about nucleic acids and the double helix structure, but because of our limited time, I am going to skip the organophosphate compounds. All right, the next part to focus on are organic bases. And with organic substances, we generally focus on this pair of electrons here. So this lone pair of electrons would allow a hydrogen ion to be accepted and attach itself here. And so we would consider this a base because it accepted a hydrogen ion according to Bronsted. Well, we've defined this before. We said a Bronsted base is something that accepts hydrogen ions. So that's one way we could describe this. We could also use a different theory called Lewis acid-base theory, but we're not going to use that in Chem 130. So we're going to focus on what we know, and at this point what we know is the Arrhenius definition and the Bronsted-Lowry definition. And in this case, this substance can accept a hydrogen ion or a proton, as we would say, and that would make it a Bronsted base. So one of the things that may kind of give away this, if you see things with an I-N-E ending, sometimes that indicates, and especially a nitrogen-based compound. Again, think about ammonia, and it's got those 3 bonds to the hydrogen, like so, and then there's a lone pair on the nitrogen here. Well, here's one of the bonds, here's 2 of the bonds, so there's your 3 bonds taken care of there, and then there's the lone pair there. All right, this is a really important reaction, and I do want you to know this reaction. This is how we make triglycerides. All right, so we have glycerol. We've already said glycerol is defined as a 3-carbon chain with hydroxy groups, and we combine those with a fatty acid. And what do we say a fatty acid is? Well, it's the carboxyl group or carboxy group. It looks like this, and it looks like that part right there. All right, so there's the carboxy group. And so when we combine a fatty acid, a carboxylic acid, with a glycerol, what happens is a hydrogen from the glycerol and a hydroxide from the fatty acid separate, and we get water formed. So every one of these is going to be a water molecule formed. So that's where we get these 3 water molecules as a product. And we get this substance, which they call a fat here, or a triglyceride. Triglyceride. All right? Where do we get the glyceride from the glycerol? Triglyceride. So fats are known as triglycerides, so you need to know that. You've got to speak the language. Fats are known as triglycerides. What determines whether a fat is saturated or unsaturated? We've talked about this already. It's saturated if there are no double bonds. It's all single bonds. It's unsaturated if there are double bonds or, well, let's just say double bonds. All right. If there's at least one double bond, it's not a saturated fat. It'd be an unsaturated fat. Now, we haven't seen this kind of structure before, but let me just take, let's say I wanted to cut this right here. All right. So we're just going to focus on what's in the box there. So each one of these points represents a carbon. So there's a carbon here, carbon here, a carbon here, and a carbon here. So this is 4 carbons long. 1, 2, 3, 4. And we know that if I cut this here, what has to happen is there has to be 3 hydrogens attached here, 2 here, 2 here, and 3 on the end here. So to make a more slimline approach to drawing large structures like this, notice they don't put the carbons in, they don't put even the hydrogens, because this is what they do. They know that if you're at a point here, like this point, and there's a carbon there, here's 1 bond, here's 2 bonds, and then the other 2 bonds are assumed that they have to be hydrogen, because we know carbon wants to form 4 bonds. So this is this is called a line formula, and it's a structural formula, and it makes it much easier to write the formula, to draw it, let's say that, and it's not as cluttered looking as even this looks more cluttered up here than this whole thing does down here. So that's the advantage of a line formula. So for this one, you don't see any carbon-carbon double bonds, so this would be a saturated fat. But if you look at this one closely, you see there's a double bond there, there's a double bond here, there's a double bond here, because there's 2 lines there. Did I miss any of the other ones here? I think that's it on the carbon-carbon double bonds. So this would be an unsaturated fat. Unsaturated because it has these double bonds. This one over here would be saturated. All right, we're skipping the phospholipids. They're important. They are. They give us things like micelles. Micelles are these phospholipids that can surround. I can give you an example. Like you got a piece of dirt on your clothes. Generally, detergents are phospholipids. The nonpolar end, this in yellow, surrounds the dirt. All right, because nonpolar dirt, like oils and greases, are attracted to nonpolar ends. The polar ends are attached out here somewhere off of this nonpolar end. So water sees the outside of this and it says, oh, it's polar. So this whole system here dissolves into H2O, and that's what happens when you wash your clothes. You have dirt on your clothes, you add detergent. This is the detergent, this organophospholipid. They surround the dirt. The nonpolar ends surround the dirt, which leaves the polar ends on the outside. Water sees the polar ends, and polar substances dissolve in water. So this goes out with the draining of the first cycle on the washing machine. Then you add water, and that rinses off the rest of these excess phospholipids that weren't reacted. And then you rinse that out, and your clothes are clean. So it is important, phospholipids, but again, not something I'm testing on. And I do want you to know these terms, even though we're not talking about phospholipids. You need to know these 2 words. Hydrophobic means literally water-fearing. So the nonpolar ends are not attracted to the water. And hydrophilic means water-loving. That means that the polar ends are attracted to water. So like dissolves like. And what we see is one end is polar, the other end is nonpolar. The polar ends are attracted to water, and the nonpolar ends are attracted to the dirt. So this is pretty much what we were just talking about. If these are the nonpolar ends, your dirt's trapped in here with these nonpolar ends, but the water sees the outside polar ends, and so therefore this substance would dissolve in water. The overall substance would dissolve in water. All right, so that's what we're looking at. So I do want you to know the terms hydrophobic and hydrophilic. So the next group of lipids. So see, lipids is a larger category than just fats. So steroids are lipids, all right? Steroids. And so what makes this a steroid is you have 3 aromatic rings here, and then you have a pentagon ring on the end here. So this whole structure here indicates a steroid, all right? So that's what you're looking for. If you see something that has this type of setup, it's going to be a steroid. And then this one is because it has probably the best known one is cholesterol. So again, you hear the all ending, you ought to be thinking this part, and then this part makes it a steroid. All right, proteins. Proteins are large biological polymers. It's made up of little pieces of amino acids, or they're made up of amino acids, okay? Your protein's identity depends upon 20 amino acids. You go, why do I need to know this? Well, this is how the COVID-19 virus works. If you're taking the Pfizer or Moderna vaccine, you have this messenger RNA. You inject that into a person, it goes into the cell produces, uses amino acids to develop a protein that looks like that spike that's on the outside of the COVID-19 virus. And so your body develops an immune response to these spikes that you have generated through the messenger RNA and the assembly of amino acids into that protein. So that if you actually are exposed to COVID, that virus's spike has already been learned by your immune system, and so it attacks it. So this is really important. Again, think about where proteins are used. Structural substances such as keratin. Keratin's what gives you your hair, nails, and skin. Specifically, what you normally relate keratin to is nails and hair, but it is that hard substance of your nail. Also, rhinoceros horns are keratin, so that's where you're going to see the word keratin. Then we have hormones such as oxytocin, insulin, and somatotropin, which is human growth hormone. And then we have antibodies. There's where we got the antibody for like COVID. So immunoglobulin is a different one, but it's that's something we can generate. And then we have enzymes that break down ethanol, or sucroses, which are sucrases, which break down to sucrose. And then we have hemoglobin, which is an oxygen transport. So those are all proteins. And they are made from these 20 amino acids. And, that's the one thing, like if you're a vegetarian, you got to make sure you're getting all of your amino acids. Make sure you're getting all of them. All right, so this is where we get into why I said amides were so important, because if you look at this, what we have is if I added a hydrogen right here, you'd have a carboxylic acid. You'd have a fatty acid right there. And then you have the ammonia group. You have an ammonia. All right. So what happens here is the nitrogen and the oxygen or carbon bond together, and then the hydrogen in one of the other oxygens breaks off and forms water, and that creates a peptide bond. Notice it's the amide, right? You've got the nitrogen. There's three things attached to it. The carbon double bond, the carbonyl group is what makes that an amide. Then we have a hydrogen, and then we have this alkyl group here, or carboxylate if you want to get technical about it. But you can see right there, this is the amide. This is the amide, also called a peptide bond. So that's why the amides are important, the amide linkages. And that's how we form proteins. We keep bonding amino acids together, and then they form these larger, and we can see we can bond here again. We can bond on this end. We can keep bonding, and we're going. And based on what we're bonding together here, we're going to get different proteins formed. The pattern that we see here is going to form different proteins. So here's how it works. The primary structure of a protein refers to the sequence of amino acids. So here's your amino acids, and depending on this sequence, that's going to determine what protein we're talking about. So if I swap these and make the proline and the glutamic acid different, just swap places, that changes the protein. All right. So based on the sequence of amino acids, we get different proteins. So they say the primary structure of this part of hemoglobin is valine. It's histidine. So hemoglobin is valine, V, histidine, leucine, threonine, proline, and glutamic acid. And again, if one of those things is out of sequence, we don't have hemoglobin. We have some alternate substance. So why we're talking about this is based on how these amino acids are bonded together, what the sequence is, that creates a structure, and we call that a secondary structure, and it refers to the shape of the protein chain. All right. And it's the result of a hydrogen from this combined with maybe an oxygen in another thing, and it creates a intermolecular force called hydrogen bonding. And that's why the protein curls on itself and makes this curlicue here. So this secondary structure, we call this a helix because it's spinning around here. This secondary structure gives this certain biological activity. So even though it's individual organic compounds that we have named amino acids that have bonded in a sequence to give us this entire three-dimensional structure, which is a curlicue, corkscrew, and that corkscrew, that structure, gives this certain biological activity. So the tertiary structure is, here are these ribbons that we just saw, but when we start to think of them in three-dimensional space, then, and we have active sites within that, and then we also have an overall shape, an overall three-dimensional shape here. That's called the tertiary structure. And it refers to the folding of the protein into its characteristic shape. So there's the curlicue. That's the secondary function. But when we take the whole thing into account, What's the overall three-dimensional shape of the protein? Then we're talking about the tertiary structure. And you go, why do I need to know that? Well, based on the way this structure is, this heme can attach itself to this protein at this point. So it's these certain holes or gaps in here allow things to interact. And in this case, we have heme attached to this protein. All right, so here's another one. So we're not looking at the individual curlicues. It's not a secondary structure. We're not looking at the carbon chains, the primary structure. We're looking at the overall structure, the overall three-dimensional structure. So this is a tertiary structure. And we can see in this structure that there are places where heme can attach more than one place. There's one, there's two, there's three, there's four. And what we really have is we go back and we see that what we actually have is we have this structure 4 times. And because we can combine these structures into groups of 4, this is called a quaternary structure. All right, quaternary. So they got each one of the proteins structures colored differently to emphasize that. It again roughly forms a spherical structure, and the heme can attach in these 4 places. All right, so we really burnt through nitrogen-based compounds, make amino acids. The sequence of amino acids determine the protein. The way the protein curls on itself is called a secondary structure, and the way the overall structures look, that is called a quaternary structure. And we can combine protein structures and get quaternary structures, but it is the structure itself, not the individual atoms per se. The structure is what has the biological activity. And like I said, this is the way we develop the protein that makes the spike shape so that your immune system's ready to take on COVID. All right, so we're switching gears here. All right, so we've talked about lipids and a subcategory fats, and that they're related to the fatty acids that come from the carboxy group that we've talked about in chapter 14, the carboxylic acids. We've talked about the amines and the amides in chapter 14, and those become amino acids, and then amino acids become proteins. So we've seen that relationship. So now what I want to talk about is carbohydrates. So in the last chapter we talked about alkanes, and we said alkanes are single bonded carbon bonds, and we talked about aliphatic and aromatic hydrocarbons. Well, we want to focus on just the single bond carbohydrate. So carbohydrates, this is the biochemistry name for carbon, hydrogen, oxygen compounds, and they're referred to as simple sugars, and this is the general form. So if N equals 6 and L equals 6, or M equals 6, and I plug that into this equation here, I would get C6H12O6. All right, because 6 times 2 is 12, and then we have 6 oxygen, 6 carbon. So carbohydrates include molecules like glucose. So again, we're speaking the language of biochemistry, glucose, and the dimers and polymers of these sugars. So the first term after carbohydrates that you need to understand is monosaccharide. What does monosaccharide mean? Monosaccharide means a sugar molecule, um, one unit of that sugar molecule, and N and M in the formula are equal. So if we look at this equation up here, if N and M are equal, we would get this sugar. So that's a monosaccharide. So to simplify this equation, we could write this equation instead, which is what we normally write. So again, if this is a 6 here, we're going to get C6H12O6. So those are going to be monosaccharide sugars. This is the empirical formula. All monosaccharide sugars are going to follow that formula. So most of the biologically important monosaccharides, they have an N of 5 or 6, all right? And those are known as pentoses or hexoses. So on the next slide, what we're going to do is we're going to link monosaccharides together. We're going to take the monosaccharide glucose and the monosaccharide fructose, and we're going to take the hydroxy group of this sugar and the hydrogen of this hydroxy group on this sugar, remove those, and those form water, and then the oxygen here links to the carbon there, and we form a glycosidic bond or glycosidic linkage. And when the two monosaccharides bond together through this glycosidic linkage, it's called a dimer of the monosaccharides, and now the entire compound is called a disaccharide. So this entire compound where we've bonded two monosaccharides together is called a disaccharide. So this reaction you need to know is called the condensation reaction, and that makes sense because what you form is water. And so water is one of the products. That's what condensation, we're taking water, producing water here. That's an easy way to remember it. Is condensation, we know we're water forming, and so we see water as a product here, and that indicates that we're doing a condensation reaction. But the bottom line is, how do we link monosaccharides together? It is through a condensation reaction where the hydroxy of one monosaccharide combines with the hydrogen of another monosaccharide, forms water, and the two monosaccharides bond together in a dimer of monosaccharides, or what we would say is it forms a disaccharide. All right, so the opposite can happen. We can also take a disaccharide and we can break it apart into its monosaccharides. So this is what happens when we digest sugar. So a disaccharide that we all know is sucrose. We also call that common sugar, right? Sucrose. So sucrose, when we ingest the sucrose, we have an enzyme that breaks apart the monomer, breaks apart the disaccharide into its monomers, glucose and fructose. So in this case, we're not taking water away. We're going to add water to the disaccharide, and that water added to the disaccharide. So these two things were bonded together. We add water to them, and they break apart into their monosaccharides. So just to be clear what's going on here is, let's go back to the previous slide. So here you have a disaccharide, all right, like sugar, and we form this sugar from these two individual monosaccharides, and that created this glycidic linkage. And now what we're going to do is just the opposite. We're going to add water to the disaccharide, and it's going to separate the two disaccharides. And what they're showing on this slide is how does this happen is they're showing that how we get this ring structure is, yes, this oxygen and this carbon bond together, and we get that bond right there, and then this oxygen and this carbon bond together, and we get that bond right there. And so here we are taking a disaccharide, breaking it to its monosaccharides, and what I want you to know is that process of adding water to break that disaccharide apart is called hydrolysis, water cleaving. And the other thing I think is really important is to remember that sucrose, table sugar is what we call it, or just sugar, it is a disaccharide. A disaccharide. And we're breaking it apart into its monosaccharides, glucose and fructose. Fructose generally associated with sugars, fruit, and so you think of high fructose corn syrup or just fructose in fruit in general, and these are processed differently. Glucose and fructose are processed differently in the body. All right, so the last slide on carbohydrates is what happens if I keep linking them together? What if I keep linking these monosaccharides together? So here's 1, here's 2, here's 3, here's 4, and I have this linkage of an oxygen between them. So when that happens and it's an alpha linkage, the glucose molecules, so the glucose, here's a glucose, right? There's a glucose there, and here's a glucose here. And when the glucose links with an alpha linkage, we get starch. All right, so starch. So this is a polysaccharide, not a dimer, not a disaccharide, not a monosaccharide. We are taking glucose, which is a monosaccharide, and keep linking them together. And that is what a polymer is. So we didn't discuss polymers in the last chapter, but all you need to know is that there's a unit, an individual unit, in this case glucose, and they are repeatedly linked together, and we call that a polymer. And so this type of substance is called a polysaccharide. All right, and so you've heard maybe starch changes to sugar, or we break it down. Absolutely. So starch, this linkage between each glucose is called an alpha linkage. And if it's an alpha linkage, then we have a starch. And you can think of cornstarch, potato starch, you can think of rice, wheat, so forth. These are all things that contain starch in them. And we're able to digest them. So we eat bread, we enjoy eating bread, we enjoy pasta, we enjoy a baked potato, mashed potatoes, we enjoy corn, so cornbread and all of those things. So they have starches in them, and we're able to digest them. Now, if this linkage is not an alpha linkage, but a beta linkage, and that's really beyond the scope of this class, but if it's a beta linkage, this is what I want you to know. If it's a beta linkage, then we don't have a starch anymore. And so instead of this being like this, it's like this oxygen bonds here with this bond, and then this bonds down like this. Creates a different linkage called a beta linkage. When a beta linkage occurs between each glucose, now you have cellulose. You go, what's the difference between starch and cellulose? Well, cellulose is what we call fiber most of the time. It's not something we can digest. Like, we can't eat a piece of wood and digest that and get the nutrients out of it. Yes, a termite can do that. We cannot do that. We can't eat cell walls and generally get much nutrients out of it. So if you're thinking of a stalk of broccoli, and the stalk itself has cell walls that make it rigid enough to grow the crown of the broccoli, we don't digest that very well. So in diets, when you hear the word fiber a lot of times, indigestible fiber, we're talking about cellulose type compounds. We don't digest them. But you can also have water soluble fibers. Those could be starches. All right. So what I want you to get out of this slide is when we link two or more monosaccharides together, they're called polysaccharides. And in this case, the polysaccharide we're looking at is a linkage of glucose monosaccharides together. If the linkage is alpha, we get starch. If the linkage is a beta linkage, you get cellulose. Humans can digest starch. Humans cannot digest cellulose. That's what I want you to get out of it. And that it's called a polysaccharide. Polysaccharide. I hope that helps, and we'll see you in the next video.